Okay, so the first talk for today, the paper we're going to talk about is this new paper called DoRA. Uh, and Actually, I'm not going to spend that much time talking about the specifics of this paper, but I did want to also do a little bit of background for people who aren't familiar with parameter efficient fine tuning. So there's lots and lots and lots of papers now about that. So this variant is called weight decomposed low rank adaptation. And you can see it's this team from NVIDIA. The paper is only about a month old. So the general gist of um, what we're going to be doing here is that you have these large foundation models that are trained on general tasks, usually with huge amounts of data. Okay, so for language models, you're talking about internet scale amounts of data, way more than you and I have, and way more than typically anybody has for a particular downstream task. So if you're trying to do sentiment analysis, or if you're trying to do question answering, you're not going to have that much sample data. So you pre-train on more general information, and then you fine tune. The problem is, though, that when you fine tune these really giant models, it's still very resource intensive. So you need gobs and gobs of memory in order to fine tune this model, and it's going to require a lot of compute. If you just do vanilla fine tuning, where you fine tune the entire model. So DoRA is one of the latest of one of these many techniques where it's now called parameter efficient fine tuning, PEFT, where it's going to require less memory and it's going to run faster. So quick background on PEFT. So the goal is to get as much of the benefits that you can from full fine tuning without paying all the cost in terms of memory and compute. Okay. If you have a large language model, probably most of you are familiar with, there's prompt engineering. So you have in-context learning, and you can just give it some instructions. So you could say, hey, I want you to describe the sentiment of the text that I'm about to give you inside triple quotes. And I want you to answer with one word only, positive or negative. Maybe you do some few shot examples. So you say, for example, given this text, you should say positive. Given this text, you should say negative. You can do that. And for certain things, that'll work pretty well. But ultimately, it's kind of limited in how much you can bake in from doing that. So if you have these companies that have proprietary data, so I'm Ford and I want my language model to understand all the different cars we have and which ones are, fast and which ones can tow a lot of weight and which ones have this and that, that's kind of hard for you to like really stick into a prompt and have really good performance. So usually you're going to do some kind of fine tuning, and then like for example instruction tuning, having something answer questions. Very difficult to engineer that with just a prompt. So a lot of people are looking at fine tuning. I'm not really going to talk about retrieval today. So RAG, if you guys are familiar, it's another thing that people do. There's two main approaches to parameter efficient fine tuning. There's one that deals with soft prompts, where basically before the first token, the first word of your text, we're going to inject some additional information into the model. The other approach is we're actually going to change the model. We're going to physically modify the neural network, and we're going to add small components, and we're going to train those components to push the model in the direction that we want. So let's first talk about prompt tuning. Okay. So 21, Lester et al. And basically the idea here is, let's say we decide we're going to add 3 new tokens before the beginning of the actual text that we're inserting to the model. If you were using actual words, actual tokens, like there's not a lot you can do with 3 tokens. Like maybe you could say, be polite, or I don't know. But if instead of using just words, if you just used like, and so in these models, the words they're getting embedded into, say, a 1024 length vector. What you can do is you can use the full dimensionality of the 1024 floating point numbers, and you can actually pack a lot more information into each of those token positions than you could if you were just using actual words. All right. So the idea is that these dense embeddings, you can pack a whole lot into just 3 or 5 token positions, a lot more than if you were actually like writing out instructions in that sense. So how do you train these things? Okay. The idea is that kind of like normal, you're going to have some text that you start with. That's a prompt. And you're going to have text that you want to say is a good completion for it. And the model's going to predict next word, just like usual, right? Cross entropy loss. But here's the idea is that normally what you do is you run back propagation and you change all the weights in the model. What we're doing this time is we're freezing all the weights in the model. And the only thing we're going to back propagate are these 3 or 5 or however many, these 3 dense embeddings that we have. So I have a picture for you that's probably a little better than me like waving my hands. On the left, you can see full fine tuning is basically where you run training and the whole model in yellow, here's my mouse, the whole model, the weights are updatable. Okay, so even though it's pre-trained, it knows sentences, it knows lots of things, you can fine tune it. And if you train it on text that's all about Ford cars, it will actually both learn factual information as well as potentially like domain specific relationships. In prompt tuning, you see now the model is shown as blue. Okay, the model is not updatable. The only thing that's updatable are these 3 little dense vectors that I'm saying imagine are like length 1024. It's actually pretty fast because as opposed to like llama 7 billion, you have 7 billion weights that you're doing, you know, gradient descent on. Now you have 3,000, 3 times 1024. Okay, there's still a lot of calculations to generate the gradients all the way through the model back to your dense embeddings here, but still it's way, way, way cheaper. And then if you're familiar with like your optimizer, Atom keeps track of momentum and things like this, it does that for every single one of your trainable parameters. So keeping track of that for 3,000 things is a lot less memory than keeping track of momentum and whatnot for 7 billion parameters. All right. Any questions about the general? Yes.
Vector is small. So are there any limitations on, so you have a foundational model, huge, and you have just small, the prompt. So what kind of limitations are there in getting the maximum benefit? And does it require your knowledge base to be input as a part of the prompt? And how can we do it in very small?
Yeah, so the question, just to summarize it in short, is about, are there limitations? It's this small little prompt. I'm saying it's 3 tokens, length 1,000 each. First, I just want to clarify. So the 1024 or whatever, that's an architectural design of the model, right? So this is something you get to choose. So I don't even remember for like llama what the model dimension is, but whatever that dimension is, that's what you're using. I'm using 1024 as an example. Ryan, I don't know if I mean, you're like Mr. Prompt Tuning, so I don't know if you have more comments on what the limitations are. And I'll try to do this, unless you want to grab this, or I could just do a super short summary for the people online.
Yeah. So I do a lot of this per word, and what I would say is the model is limited to all of the stuff that it's soaked up, but it's been soaking up 1 trillion tokens. So typically it can get the output that you want, and you just need the right way to prompt it to trigger that behavior. And so this actually can get very, very high levels of accuracy at pretty much anything that you would expect the model to be able to do out of the box. And it's just better than prompt engineering, because prompt engineering, you're limited to the discrete token. And with the dense vectors, you can do a whole lot more. So there are certain things where it's like, if a model was never exposed to that kind of input, you would probably still struggle to get it out of prompt tuning. But in reality, they've absorbed so much data that very often, like prompt tuning is, you can get the most out of this. And if you do, right now Ted's talking about 3 or 5, but you can have more. So you might find that 3 tokens isn't enough to actually represent the complexity of what you're trying to do. So you can extend that to be, I'm going to do 128 dense vectors to represent the thing that I'm trying to do. And that can encode a whole ton of information. So that's the way that I think.
Cool. All right. So to summarize briefly, what Ryan said is that prompt tuning can do pretty much anything prompt engineering can do. And when the model was pre-trained on 1 trillion tokens, you can get any of the capacity capabilities that were baked into the model from that. So for example, if you just wanted to tell the model, talk like a pirate, 3 tokens is probably enough to train it that whatever it outputs, it needs to go R, blah, 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 matey, and talk like a pirate. But if your model was trained only on English and you want it to do more things in French, then that's something that it's really going to struggle with because you're not going to be able to add that much capability. Ryan also mentioned that for a very complex task, you might choose a much longer prompt. So you theoretically could have 128 as opposed to just 3 or 5, which is what I'm talking about. All right, any other questions? Okay, so we're not really going to talk about prompt tuning today, but that's like the general background. This is one of the methods that you see. And if you think about this, the idea that you're just sticking something in front of it, well, if you have a batch and you batch 8 different requests from different users, theoretically, there's no problem with you prepending different things for each one of those 8. So that's what they're showing in this diagram, is that hypothetically, you could have the Ford company prompt tuning thing, and then you could have the, I don't know, Genentech prompt tuning thing. And if user 1 is asking about Ford cars and user 2 is asking about some Genentech thing, you could just prepend those and you could mix them. So that's like a potential benefit of using a technique like this. It doesn't require you have dedicated hardware just for one particular use case. There's some variants. We're not going to talk about all of them, but just so you know, terms that you're likely to hear. So prefix tuning is a technique where instead of just having, let's say, 3 dense embedding tokens, and those embedding tokens will just flow through the model like normal. So if your model has 24 layers, then they're each going to get processed just like any normal word or token would get processed, and they'll go up through the layers. Instead of doing that, what prefix tuning does is it learns special values at every layer. So the 3 tokens do not flow up. Rather, you use these hard-coded values at every layer. And the idea there is you have a little more horsepower that we don't necessarily know exactly what each layer is doing, but if particular layers have a function, then you've got specially trained. And so I haven't done much with prefix tuning, but you could imagine that because you're training a lot more things, that maybe you don't need as many tokens. Maybe something that kind of works with prompt tuning with 5, maybe you can get away with 3 with prefix tuning, because again, you don't just have the 3, you've got, let's say, 24 times 3 weights that you're training. There's also one called p-tuning. I haven't spent a lot of time, but the idea there is, in the previous slide, I showed an example where you might have different prompt tuning dense vectors that you're inserting at the beginning. You could have a small model like an LSTM that's choosing what thing you should actually stick in there. And so instead of having it be very hard-coded, like Ford Motors, insert this, the model, the LSTM could kind of take a look at your question and decide based on, oh, this is like a question answering thing, so I'm going to insert this. Or if this is more of a I don't even know, like a reasoning thing, then maybe I use a different prompt or something like that. And then I'm sure there's even more variants that I'm not familiar with. So that's one side of the house. That's the soft prompt side of the house. The other side of the house is we're going to modify the model. So the seminal paper for this is the Hulsby paper from 2019. And what we're going to do is we're going to add small components to the model. When we train the model, we're going to freeze all the original parts, but the small parts that we've added, these are the only ones that are trainable. So once again, by having a smaller number of trainable weights, it's going to take up less memory, especially on our like atom optimizer. And so hopefully it'll be faster, less cost for us to train these models. If you see here on the left, this is like a zoom in on the inside of a transformer. It doesn't look like the standard transformer diagram, but basically what you can see here is there's multi-headed attention, which is the bottom half of the transformer, and there's this two-layer feed forward, that's the top half of the transformer, okay? And if you can see the colors, they're inserting a yellow box here, an adapter here, and they're inserting an adapter here. And what does the adapter itself look like? That's pictured on the right, okay? So basically it's just like a two-layer fully connected, but small two-layer fully connected network. The specific architecture of this isn't super important. The idea is that you're inserting small things that can kind of do minor corrections to the information that's flowing. So you don't want catastrophic forgetting, okay? You don't want to completely lose the model's original behavior, but what you can do is you can do slight tweaks with this. Adapters, when they tested them, the performance was pretty good. So you can get performance similar to full fine tuning while tuning many fewer parameters, like say 5% as many parameters, okay? But there is this downside to it that the adapters are bumping up at inference time the amount of memory that you need a little bit, because this 5% is now added on top of whatever your original model was. So if your original model was 7 billion, 5% of 7 billion, still what, 35 million or 350 million, right? So 350 million. So it's like it's not chump change. The other thing that people found in practice is that, let's say you've got this big language model and you have these model dimension 1024, and you have these 1024 by 1024 weight matrices for like Q, K, and B and stuff like that. When you actually go to run this thing, the code will basically figure out how to break this down and run it on your GPU, okay? And something like a big 1024 by 1024 matrix multiply, it actually knows how to do this really well. And so it can pipeline this really, really well. It breaks it up and it figures out how to do whatever, these little tiles and multiplies, gathers, all that kind of stuff. But when you have this, and then you have this tiny little adapter that you need to do and like add it or whatever, does not pipeline as well. So in fact, more so than just the 5% penalty of more weights, people found that the inference performance was more than that, because it actually just broke up the pipelining operations of the LLM. I'm sure that somebody could have spent the energy to figure out a way to cleverly improve the pipeline, but naively, that was one of the problems people ran into. So they said, well, we like these adapters. They have pretty good performance and it's still cheaper, but wouldn't it be nice if we didn't have to pay this penalty when it comes time to actually run the model, when it comes time to do inference? So probably a lot of you have heard of LoRa, okay? So low rank adapter. The idea here is that this adapter, when you have weights shown here in the blue, it's going to add something instead of like above it or below it. It's going to add something beside it, a small little component beside it. And during training, you're going to do the same thing as a regular adapter. You're going to freeze the original weights, and then you're going to only train the small thing. On this diagram, the orange doesn't look that much smaller, but this thing can be quite a bit smaller. It can be hundreds of times smaller than the regular weights. You're going to train it, and then what you do is each of these little orange components, when you're done you multiply the A and the B together, and it's going to give you the same shape as your blue regular weights. And then you add the two of them together. So two matrices of the same shape, you can add them together. What's really cool about this, though, is that when it comes time to do inference, you don't have to physically keep the blue and the orange separate. What you can do is you can multiply out the orange, you can add it to the blue, and then that new value, you just replace the blue values with. All right. And so this was the clever insight that we're adding a little something, but we're adding it in a way that when we're done figuring everything out, we can stick back new weights into the original model, and the model's architecture is completely unchanged. This is shown here for square weights because that's what you tend to have a lot of in a transformer, but it works perfectly fine on rectangular matrices as well. They do not have to be square. Okay. And the idea is that you have a D by R matrix and an R by D matrix. And when you multiply them together, you get a D by D matrix. It's lower rank. So it's not full rank. So it's not all possible D by D matrices are representable, but you can choose your R. And so in the extreme, if you choose R equals 1, so then say for a 1024 by 1024 weight matrix, that has 1,000,000 floating point numbers, but LoRa would have only two 1,000 length matrices. So you're going from 1,000,000 down to 2,000. If you choose something like R equals 5, then you're going to have 10,000 weights instead of 1,000,000 weights. So again, you're talking about like 100-fold reduction in the amount of trainable weights. LoRa had pretty good performance. Yes.
Why is it initialized on a normal distribution? You know, is that just like sort of just the obvious thing to pick, and so that's why they did it, or is there like a theoretical reason for it?
The question is, why is this A matrix initialized with a normal distribution? I don't know the answer explicitly. We tend to initialize everything with normal distributions, right? But the interesting thing is the way it works is this B gets initialized to all zeros. And when you multiply the two of them together, initially what you do is you get all zeros. So that means that when you add this to your pre-trained weights, nothing happens. So the model starts out exactly with the original model. But as A and B slightly modify, then that allows the model to vary. Okay. So I think I covered this. So for training, this product of low rank matrices sits next to it and gets added in. But once you're done training, what you can do is you can just take that product of the two orange and add it to the blue, and the new blue prime, that becomes your new weights. So there's zero inference cost, zero change. There is actually other possibilities people talked about. I don't know if people are really doing this. But on a GPU, when you're doing inference on something like a large language model, it turns out that the actual matrix multiplies, even though you're sometimes multiplying pretty darn large matrices. Turns out that these GPUs are so fast that that's actually not the bottleneck. So if you say multiply two 16,000 by 16,000 square matrices together, it actually can do that blazingly fast. You know what takes it a really long time? Loading a 16,000 by 16,000 matrix into its core to actually do its thing or whatever, right? Or loading that 16,000 by 16,000 matrix from main memory, CPU, right, onto your GPU. So in fact, since memory loading is actually the real bottleneck, they said, oh, one thing you could do is you could have those blue weights like queued up as like your sort of your starting point, and then the small little orange weights, because they're so much smaller, if they're 100 times smaller, it'll be 100 times faster to load them onto the GPU. And actually like multiplying them and adding them onto the blue weights, that's super fast. GPU can do that in the blink of an eye. And so you could actually sort of on the fly switch between different LoRa's. So my Ford LoRa and my Genentech LoRa, they're not loaded simultaneously, But the idea is that it might be faster than you would think to switch amongst them, because really the bottleneck is the memory copying. It's not actually all the multiplies. When you do LoRa, you can do this on any rectangular weight matrix in the model. Technically, you don't have to do it on every single one. So in the original LoRa paper, they did experiments and they said, yeah, for the best performance, you would do it on all of them. But it turns out that if you have Q, K, V, and feed forward weights all in your transformer, that really, like, if you picked two of them, if you did like, you know, Q, I don't actually remember if it was Q and O or if it was Q and feed forward, but basically 2 out of the 4 was like half as many trainable parameters, but it got you like 96% of the performance of if you did all of them. And so there is a little bit of theoretical fine tuning you can do in terms of how many places do I want to apply this LoRa. And because LoRa was so successful and people love the fact that there's no inference cost and it's very intuitive. In fact, someone might have given you a model and they used LoRa to fine tune and tweak the weights, and you wouldn't even know because it just looks like any other normal model. You get the model, you get a set of weights. You know, it's that easy. So because of that, there's been all these different successors. Okay, so QLoRa adds quantization. There's other ways. Instead of these 2 matrices being multiplied in the original LoRa, you could do like Hadamard, Kronecker, blah blah blah. And then there's this Vera model that was proposed and talked about in today's paper, where they actually did some like random vectors. So I've been talking about like 1024 length vectors, right? So they have these like length 1024 vectors that they use, and they share them across all the layers. And then you have only this very tiny number of weights that let you just, so like, let's say you did rank 5. I think then you just have like 5 weights per layer where you get to just adjust up and down this preset. And so it's like 1,000 times fewer parameters than regular LoRa. Some crazy, it's like way, 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 way less. And it actually worked pretty well. So so just a whole lot of different variants. I wrote on the slide countless. I mean, I don't know. If you did a search, there's probably hundreds, if not thousands, of different variants that people have come up with. All right. Any questions about LoRa before we actually get to today's topic, which is DoRA? All right. So here's the concept for DoRA. So what are we going to do different from LoRa? What's our flavor for this? What we're going to do is the original weights that I've been talking about as just this generic square, could be rectangular, but this generic square matrix. We're now going to decompose that. We're going to have these 2 concepts that they call direction and magnitude. So if you're familiar with like linear algebra, whatever, you know, they talk about you have your orthogonal vectors. Okay, that just means that, you know, the dot product 0, but you can have length 1 and then you have orthonormal vectors. And so when things are length 1, then that sort of simplifies certain things or whatever that you can do. And so in this case, what they're saying is, I'm going to change my weight matrix so that every column is length 1. And then I'm going to save off what is the scaling factor that I need in order for each column in order to make them length 1. Okay. So I'm going to save off the length of each column, and then I'm going to divide each column by its length so that now they're all unit length. So the scaling factors we're going to call the magnitude, and the columns that are now all length 1, we're going to call the direction. Okay. So a little bit of intuition here. So imagine that you have just rank 1. You have 1024 times 1024, and you're going to make a square matrix. If part of that square matrix has numbers that are really small. One column has numbers that are like 0.01. And another column has numbers that are really big, 10. You're now talking about 3 orders of magnitude difference between those 2 columns. You can imagine it might be a little bit difficult for this rank 1 thing to approximate these guys where, one column is just so much smaller than another column. Okay. So that's kind of my intuition for how it might be helpful to say, let's like scale this weight matrix so that they're all sort of similar in size and then split out the whole magnitude. So there's other papers that have talked about doing this decomposition, and you can just do this for the original training of the model. And it's like, if you get it to work, it's helpful because again, now you just have this nice scaling where all of the direction pieces are like similar in size. But my understanding is they had trouble getting it to work from scratch because this random initialization and getting everything to work, it was just very, very finicky. Okay. But for fine tuning, we don't have this cold start problem. We're not starting from scratch with randomly initialized weights. We have a trained model that actually has very good weights. And so turns out that it didn't seem to be so finicky for this fine tuning use case. So what do? I have a picture on the next slide, but just to kind of verbally talk through it, when you're doing training, these magnitude vectors, they're 1-dimensional, not 2-dimensional. Okay, so they're much, much, much smaller than the direction ones. And so they say, just do regular backprop on those. Just do full fine-tuning training on those. The direction matrices, they're big. They're still 2-dimensional. So we're going to use LoRa for those. We're going to freeze them, and we're going to do LoRa. When you decide you want to do inference, what you can do is you can do the work of recombining everything so that you no longer have separate magnitude and direction or whatever. You just have one regular weight matrix, and then voila, just like LoRa, now you don't even know that they ever split it out and they did this fancy training because all you see is just a normal looking weight matrix. So here's the picture if you had trouble sort of following me, like talking about it verbally and waving my hands. So in the upper left corner, this is the weight that we came from the pre-trained model. Okay, just regular old. It could be rectangular, but it looks square on this diagram. Okay, so what we're going to do is we're going to take each column of this, we're going to normalize it, and we're going to save off those weights. If you look at the notation here, you'll see in green the magnitude. This norm of our weight matrix, the little lowercase c, is their made-up notation to say do this by column. Okay, I don't think this is a standard operation, but they're just saying little c means take the norm of each column. Okay, and so now this is a 1 by, this is a vector, this is not a matrix. The direction thing is the same shape as the original one, okay, but it's all each column is just a norm. So the lower left, this is our plain decomposition. We haven't done any training yet. This is just how you could decompose any matrix into a magnitude and a direction. When we want to do the training, what you see is they add LoRa here. So you're familiar with the little, if we put trapezoids to the right of something, that means we're doing LoRa, okay? So we're going to do LoRa for this guy down here. And the magnitude, we're just going to train like any kind of weights. We're not going to freeze these. We're going to let them train. When you're done, you could do the whole thing where the LoRa trapezoids, you multiply those together, you add those to the blue square, and then you multiply the blue square by the magnitude, and voila, you just get a normal set of weights in the exact same shape as what you started with. And like I said, the person who receives this can be none the wiser that you had to do all this work while you were doing training. So that's the technique. I have one more slide to say, what's the intuition? Why did they bother this? I gave you one intuition in terms of like the columns, some of them being big, some of them being small, might be a little weird. The authors were interested in this idea, and they took a look at what happens when we do full fine tuning and what happens when we do LoRa. And on the right, what you can see is that it's not theoretically required just because LoRa breaks it up into two low-rank matrices. But even though it's not required, what ends up happening is anytime there's a big change in direction, there's also a big change in magnitude. And anytime there's a big change in magnitude, there's also a big change in direction. You can't have something just change direction a lot, but stay the same length. And you can't have something that grows in length a lot, but stays in the same direction. It's theoretically possible. It just doesn't ever seem to happen. If you look at how closely all of these dots are on this blue line here, okay? What happens in reality is they're kind of decorrelated. Like, yeah, sometimes the direction changes and the magnitude changes. Sometimes it doesn't. Sometimes, so they said this is the problem. People assumed that the gap between lower performance and full fine tuning was because you were using a low rank. And they're saying, aha, part of it is because you're using a low rank approximation. But actually, this phenomenon here means that you're getting hurt no matter what, even if the low rank approximation were super duper good. So what do? We do this decomposition so that you're training the direction all by itself, and we have this separate magnitude thing that we're training, and we let the two of them vary. And when you do that, then all of a sudden you see the picture on the right for DoRA. Now it looks, it's not exactly the same, but it looks, more similar. It's a slightly negative slope. It's not the exact same, but you can see there are points that are like sort of, varied around, and you can have, for example, a large direction change without changing the magnitude. That's one of the key things that you want to be able to. Yeah.
Do you know that in the DoRA paper, did they do any experiments? I don't know. But did they do any experiments where they tried doing LoRa, increasing the length, the rank at each time, seeing what the performance increase looks like, and seeing how many number of ranks above the thing DoRA is equivalent to? Like, how many ranks does it give you in terms of new performance?
Yeah, so the question is, did they check to see if you tried different ranks and bigger ranks, what the impact is? Yes, there's a slide. It's not necessarily exactly the way you were setting it up, but there's a graph that we'll see in a second that shows the impact. Any other questions? All right, so here's some real world results. So by the way, I think it's very good that they have real world results. So one thing you'll notice is that when you train, you're often seeing the loss in terms of like cross entropy, the loss in terms of like perplexity. Perplexity is not a good test for downstream performance. You need to actually take the LLM and have it do reasoning, have it do question answering, have it do translation, have it do sentiment analysis. You need to actually have it do those things, because you can have a very low perplexity, but still not have a very powerful language model. So here they have a bunch of different tasks. And you can see that they're comparing it to prefix tuning, the first adapters I showed you, the Goolsby adapters that are done in series, Goolsby adapters that are to the side, that are done in parallel to regular LoRa. And then they have two DoRAs. The first one with the dagger is half as big as the LoRa, which is why if you notice the number of parameters is approximately half of what LoRa has, okay? So they say we're gonna handicap our thing by giving it half as many parameters to just really show that even at half the size, it beats LoRa, which is pretty awesome. So it means that, you can either get the same performance with something that's half the size, or you could get better performance by going for something that's the same size. All right. If you look at this table, I think that this is kind of crappy. They said, we're going to show our results in bold, whether they're the biggest or not. Like, what? Who does that? So they did say in the text that they didn't do as well with the half-size DoRA at 80.8 as the parallel adapters. But if you look here, what you can see is the parallel adapter requires almost 3% as many parameters as the original model. And this DoRA model is at 1/3%. So it's 10 times fewer parameters. And so I think it's fair to say that DoRA did a great job in that it almost got the same performance with 1/10 as many parameters as the parallel adapters. But if you're writing a paper, if you're going to bold something, bold the biggest numbers, not just your numbers. Okay, that's a pretty standard convention. There's some other tasks. I'm not going to like go into super detail on all of them, but they looked at some multimodal models. So they had a vision task, they had a video task, and then they did instruction tuning on Lava, which is another language vision multimodal model. And you can see that in all cases, DoRA beat the LoRa fine tuning. In some of these, it actually was quite competitive with full fine tuning, which is pretty awesome because you can see here, like this is at 6% of the parameters and you got the same performance as 100% full fine tuning. And here it's 5% of the parameters, same performance. Yeah.
I'm guessing the time it takes to run is pretty much the same, right? It doesn't really take any time to scale it.
The time it takes to fine tune DoRA versus full or versus LoRa or
DoRA versus. I don't see
DoRA
any reason there should
versus
be a big
LoRa, I believe that where DoRA is say 5.96% and LoRa's 5.93, that 0.03 is how much slower it's going to run because it's training those magnitude vectors. So it's training this itty bitty bit more. But so like if you look at that 0.03 versus whatever, I mean that's like less than 1%. So it's probably like 1% slower than LoRa, which is no biggie. And you could then shrink your DoRA potentially, and then you're running faster. All right, so here is, oh no, one more slide after this one. Okay. They also looked at this Vera method, which was the one I said that had these sort of random vectors shared across layers and scaling. So if you look at LoRa on Llama 7 billion has 2.3% of the parameters, but Vera is like at 0.02. It's 100 times smaller. Okay, so this is a very different approach. But what they showed basically is that DoRA works better than LoRa, works better than Vera, and you can actually add DoRA to Vera. And so then they called that DeVora, whatever. And they were able to improve the performance of Vera. In this case, it kind of looks bad in that it doubled the number of parameters, but it's because Vera is already so tiny that these magnitude vectors actually are in the same ballpark as the size of Vera. So, but I think it's fair to say going from 0.02 to 0.04%, you're talking about, it's still less than 1,000th the number of parameters of your original model, and it's pretty good. And so then you can see on the right here, they said, does this technique only work if you have lots of training data in order to have like really good data to teach it what to do? No, basically, DoRA's the green line, and at small amounts of data, it does better. At medium amounts of data, it does better. And full data, then DeVora and DoRA were similar, which is kind of crazy because DeVora is like 50 times fewer parameters. But anyway, so they're saying this isn't a technique that only works if you have lots and lots of data. It seems to work in all the regimes. And then the last performance slide, this was the question that came up earlier. What happens if you try varying? So they didn't try huge numbers of things, but LoRa here, you can see the performance on, I think this was just Llama 7 billion. 4, 8, there's a pretty big jump when it goes to rank 16, 32. I don't know why it goes down with 64. But so they're showing there's this massive gap at 4 and 8 between regular LoRa and DoRA. And then you can see that DoRA at 4, LoRa with 16 actually does beat it in performance. So whatever, you can't necessarily interpolate, but if I were just to like guess, right, like LoRa with maybe 12 would be about the same as DoRA with 4. So that's a pretty impressive gain. Then the final thing they talked about is that I mentioned for LoRa, you don't technically have to do LoRa on every weight matrix just because you have them. Okay, you can do just the Q and just the V or something like that. So with DoRA, you now have two choices. You can do, am I going to do DoRA on it? Or also, am I going to do just the magnitude and not bother with the direction part? I mean, technically you could do the direction, but not the magnitude, but because the direction is like 99.5% of your cost, you wouldn't do that. If you're going to do that, you just do the whole thing. And they actually found that, oh yeah, I can sneak in just a couple directions and then a few DoRAs, and I can actually get a little better performance, and I don't have to do full DoRAs every place that LoRa does. They don't have a wide set of results. I didn't look in the appendix to see if they had more, but again, just the general idea that it does give you some options, and that maybe if this technique works really well, maybe people will play around and you'll see more tests done by follow-up research, kind of how to optimize where to do it, where not to do it. All right. So in conclusion, the authors found that that LoRa has this pathology that large changes in direction have to be accompanied by large changes in magnitude. That it just, for whatever reason, it doesn't seem to be able to learn without doing that. It's theoretically possible, but it just doesn't happen. So they do this decomposition thing. They consistently beat LoRa. They try different models, different tasks, different number of rank settings. It's nice that they tried Vera, so then other variants on LoRa might also be able to be combined with this decomposition technique. So it might generalize. And more to be shown, but again, you can choose what parts. So so you might not need to do full DoRA in some places. You might just do magnitude. I was a little surprised, actually. I didn't think magnitude alone would really kind of do much, but it seemed like they could get away in a couple places doing magnitude only, and it seemed fine. All right, so I will share, I don't know, like in the Slack or whatever, link to the slides, but I do have references to some of these papers. So the Hoolsby, the prompt tuning, LoRa. If you're doing stuff on Hugging Face, they have a whole PEFT library now. DoRA's not on there yet. The paper's only a month old, but tons of good stuff if you're trying to do fine tuning and you don't want to like spring for an H100 or something like that, or probably even more than one. I mean, Llama 7 billion, I forget, but I think it's like you multiply by 16 if you're doing Atom. So 7 times 16 would be over 100 gig of GPU RAM you need. So you'd need, I think, 2 H100s or something. And then the Vera paper. All right, so let me turn things over to Ryan. Any final questions on DoRA? All right. All right, give us a second for technical stuff. We need to like switch over to Ryan's slide and all that kind of stuff.
There we go. this one. All right, thanks everyone. So I'll be talking about the Mixture-of-Depths paper. Is anyone familiar with Mixture-of-Experts? Is that familiar? Okay, a few people. Okay, I'll describe it anyway. So Mixture-of-Experts is this idea of you have a model, it's got a certain number of parameters, you can kind of split it up into a certain number of pieces, and then
One of your.
true. But you have your model, it's split into potentially sort of 8 pieces, and then instead of doing all computation all the time, you use maybe 2 of those experts at a time. So you train all 8 of your experts, but you might at inference time only use 2 of them. So then you end up with this model that ends up a quarter of as much compute. And so Mixture-of-Depths is this new idea of trying to do this across a different axes so you can get efficiency out of that instead. So the problem that they're trying to tackle is that there's a whole bunch of wasted compute in these transformers. So when you're doing these transformers, it's attending to all tokens against all of the other tokens. And in reality, a lot of that is probably wasted because you don't need to attend to the same tokens many times, and often the interactions between them probably doesn't really matter. And so what they were trying to figure out is how do we do this Mixture-of-Experts things, but across the token so that you're not doing attention across everything all the time. So they came up with this Mixture-of-Depths idea. And basically the idea was instead of doing all the tokens all the time, we'll have a router layer that will then figure out which tokens do we want to look at which time. And they found that they can actually cut compute by like half using this. And you can then combine that with the Mixture-of-Experts thing. And then you're saying we made it a quarter because we did Mixture-of-Experts, and we did half because Mixture-of-Depths. And then you all of a sudden have a like much smaller compute footprint when you're actually doing things. And so this is showing you have the router layer in the front, and that might just block something from being added to the attention calculation. And so that can save you a bunch of effort. And this is what sort of that access pattern might look like. You might see that actually a lot of these are just skipped over, basically, or they're just passed forward. They don't actually do any attention on them. Yeah.
Sorry, and how do the router layers work?
I'll talk about it in later ones. So there's a whole bunch of different routing schemes that they came up with, and they were trying to figure out what's the best thing to do. And so they were looking at the trade-offs of these different approaches. So if you look at the token choice routing, that one on the left, it's basically saying per token, decide which expert to send it to. And they realized that this was kind of a problem because you might have certain experts that are overutilized and you might have other experts that are completely underutilized. And then you end up in the same problem where it's like you might have one expert that gets everything all over again, and you might have one that has hardly anything. And then the other approach that they were looking at was doing per expert. So they have each of these experts, and then they say each of you is going to get the top K tokens. So if originally it was going to get 1,000, pull out the 512 that were most relevant. And that was useful, but you could end up with similar problems and lots of tokens being reused multiple times in different experts. And so what they ended up deciding on was doing a more global selection where they basically said, we'll just set a certain top K, and they figured out we can do 50% or 12% or something like that, and they could kind of ablate that. And that gave them the direct reduction of calculation that they were going to do. And that saved them from all of those other problems, is just do a global, like I'm only going to pull the top 10% or something like that. So the results that they got was that they got much better performance per flop. So what ended up happening is if you say I'm only going to do 10% of the attention, then you can do way more forward passes for amount of compute you have. So if you have 8 H100s and you want to train for a month, you get better results out of this because you're able to take a lot more forward passes and you're able to have a bigger model, and all of that stuff. And so these curves over to the side here is basically showing the various different levels of reduction. So they found that they could reduce it all the way down to 12% capacity. And this is the curve of as you make bigger and bigger models, and then you're lost. So you want a lower value. And so they were finding that with this reduction, they were able to do a bigger model. And then for the same amount of compute, they were able to get better results out of it. So for example, they could do like a 500 million parameter model, and they could get better results out of that than they could with one of these other options along the spectrum. A lot of people have done work on the laws of scaling. So figuring out, given a certain amount of compute, how do I get the best possible model? How do I trade off the size of the model, the amount of data that I train it against, and all of the other tricks that you can throw in there. And so they were finding that this mixture of depths actually let them go further along that frontier and get even better performance out of it. And at the same time, you're doing that reduction of the attention that you're doing. So at inference time, you get a big cost saving there as well. So here's another one of the graphs that they showed. And like I was saying, it let them do more training steps. So even though you're reducing the amount of attention that it's doing and the amount that it's learning per step is less, because you're able to do way more steps, you're able to make up for that because you're able to do more training given a certain budget, basically. And so this is them showing a few different lines saying, here at this compute budget, we go along the curve this way, and we find that the mixture of depths is best. And then we have a different compute budget, and we find that it's the best still, and then another compute budget, and they find that it's the best again. So they were able to prove, like, across all of these different settings, it was able to create models that were the best. It doesn't necessarily guarantee, because you can get the wrong trade-off in terms of compute versus size and data and everything. But in reality, they were finding that it's possible to get better results out of this. So here's an example of what the routing pattern might actually look like. So what they figured out is that you want it to be alternated. So you have one layer that is full attention, all of the tokens attended to, and then the next one, you do that reduction step. And so there's a combination between full attention and that reduced attention with only the tokens that get routed through. And the way that this actually works is if a certain routing choice is made, then the attention is actually calculated. And if the alternate choice is made, then it's just the identity. It just passes the token directly through. So no attention is done to it. It's just continued forward. So all of these greens, they're calling it a round block. It's just basically saying, just echo this to the next layer. Don't do any calculation onto it. And so these blue ones are saying, actually attend to this and do your calculation on top of it. And so this is what the attention pattern might look like when you're saying only do 12.5% of the actual attention, pull out the top 12.5% of the tokens. And so like I was saying, they can actually combine this. So they can do mixture of experts and mixture of depth. And then they're saying split the model into 8 pieces. And then on top of that, only do a certain number of the tokens at a given time. And then with that, they're able to get a model that is significantly further on that axis of performance per compute. And it also gives them the benefit at inference time because you're doing that reduced calculation. So you can have a theoretically massive model, but you're doing much less compute and you're getting much more value out of it. So these are all of these different plots. So showing, here's the baseline, how much performance we're getting per flop. And then you can see that they add in the mixture of experts, and then they add in the mixture of experts plus the mixture of depths. And you get this result that's significantly lower than the previous one. And they toyed with various different schemes of this. So one of them is having the routing beforehand on the mixture of depths. And then the other one is having it mixed in on top with the mixture of experts, where one of the expert options is basically just identity. So instead of actually applying one of the experts, you just say, go do the identity. And they found that both of those really worked well. I think that's all I've got. Questions? All right. Thanks, everyone.